Hello, and welcome to the lecture on standing waves. Here we're going to be talking about sound waves that are confined to a string or to a tube. Okay? So let's discuss that idea. Now, if we're talking about waves on a string, it's more of the sound that that string is going to create as the vibration travels from the string into the air. But when we talk about sound waves trapped in a tube, like a wind instrument, then it is quite literally the sound wave inside the tube. But in both cases, the ideas are closely related to sound and also to ideas in music, although we won't be getting into any official music terminology. Okay, so since we're talking about stand waves and this idea of waves being confined to a particular place, which is a standing wave, then we should start with a concept that encapsulates both the standing wave idea and the sound wave idea. And I feel a great way to start with that is explaining the difference between what is a pressure node and a displacement node. Okay? So this terminology refers to sound waves resonating in tubes, all right? I often think of an organ, right? Because we have such a very direct example of a tubed instrument, right? So an organ with many different length tubes. Okay? And the idea is that there are pressure nodes and displacement nodes, and they have a quarter wavelength or pi/2 phase shift between them, which on its surface probably seems a little abstract, but let's dive into that idea and see what I mean. Although let's first appreciate that the idea of having a quarter wavelength being equal to pi/2 is an important concept because, of course, a wavelength is a full repetition and so is 2 pi. Okay? So you divide either in by 4 and you've got a quarter of a full repetition. Okay, so look at this picture. I think this really shows a lot of what's going on. All right, so I'm going to also explain the concept of a node. So let's think about this. All right, so let's start with this case up here. Here we have a tube with 2 open ends. All right, so this would be like a flute, open end here and an open end here. So that means at either open end where the confined gas or air really inside of this tube is in contact with the outside world, there must be a pressure that is equal to the atmospheric pressure. Okay? Because if there are pressure variations within the tube due to the sound wave being a longitudinal wave that does precisely that, affects the pressure, well, that's fine within the tube, but there's no way that it can create any pressure other than a pressure equal to the atmospheric pressure outside of the tube. Okay? So in other words, in the open end. So that's what we call a pressure node, because that is a baseline pressure. Think of a node as an equilibrium. And to elaborate on that idea, let's look at this middle point, which is a displacement node. Okay? So a displacement node represents a point of complete destructive interference. Okay? So nodes are total destructive interference. All right? So let's write that idea. A node is complete destructive interference. Okay? Well, we're familiar with the idea of wave interference and wave superposition from previous lectures. So we know that to have complete destructive interference, you have to have 2 waves that are out of phase. Specifically, they have to be a half wavelength or pi radians out of phase. Well, how would we achieve such an out of phase nature? What 2 ways are we talking about? Well, the idea of every standing wave, again, the title of the lecture, every standing wave in this lecture is that there is a wave traveling one direction, a wave reflecting off some interface, and a reflected wave traveling in the opposite direction. Of course, that reflected wave will eventually make it to the other end of the confined system, reflect off another interface, and then itself become the reflected wave, having been the incident wave. But the point being that is that at any moment in time, there's always a wave traveling to the right and another wave traveling to the left. One reflected, the other incident, right? But the idea is there's always 2 waves crossing over back and forth across each other. And if their velocity and their frequency exactly matches the actual physical length of your tube, or we'll see in a second, the string, then you have what's called a standing wave. And it turns out that in order to get those conditions just right, you have to balance the frequency, the velocity of the wave, and the length of the tube. And in this case, the picture I'm showing is what's called the fundamental standing wave. that is the longest possible standing wave that can exist in a particular system. So let's look at this, because as we were talking about a moment ago, here's a tube with two open ends. At each open end is a pressure node, an equilibrium point with pressure equal to the outside pressure. That makes sense again, right? Equilibrium. Then in the middle is what's called an antinode. And an antinode represents the maximum amplitude away from equilibrium. So in this case, this would be the maximum deviation away from atmospheric pressure. It would be the greatest positive pressure, okay? And it would also be the greatest rarefied part of the gas, so the greatest negative pressure. But it would oscillate between the two, and it would always be the point of the greatest variation away from atmospheric pressure. Whereas, of course, the pressure node just stays always at atmosphere, all right? Now, let's compare that to the idea of displacement shown in pink, because the displacement has a node at the middle. What does displacement mention, or what does it represent? Well, displacement actually describes the back and forth motion of the molecules that compose the gas through which the sound wave is traveling. So the idea is that in the middle of the pipe, the actual molecules, they can't move back and forth. They are varying between maximum pressure and minimum pressure, but they're stuck in place. There's no actual back and forth motion of those molecules. Whereas the molecules at the far end, they're free to move, and they are going to slosh back and forth. Now, they're going to slosh back and forth at equilibrium pressure, but they're going to move the most. So they're going to experience maximum displacement. So we see the open ends of any tube is an antinode for displacement. And then we see that it makes sense for antinodes of displacement to be exactly where nodes of pressure are. And that's always the case when we talk about standing sound waves. A pressure equilibrium point called a pressure node always equals a displacement antinode. So to say that in other words, any point where the pressure is fixed is a point where the molecules are free to move. Any point where the molecules are not free to move and fixed in place, the pressure is free to variate. Okay? So that's the idea. And that represents that pi over 4 or lambda over 4 or pi over 2 phase shift, because every pressure node is exactly 1/4 wavelength away from a displacement node, because it's always the distance between a zero and an amplitude. And we know from our sine wave that to go from 0 to an amplitude is 1/4 of a full wave. See? 1/4. Okay, so that's the phase shift between pressure nodes and displacement nodes. And to think about sound waves, you need to think about both types of nodes. Now, back to the idea of the fundamental. Because for this particular standing wave, the superposition of two waves, one moving to the left and the other to the right, well, in order to create that standing wave, as I said, you have to have a fine-tuned combination of velocity, frequency, and tube length, right? And also string length, if we're talking about strings. But here we're talking about tubes. Well, with that in mind, why is this particular picture the longest possible wave? Because that's what I said. The fundamental is the longest possible standing wave that can exist in this particular tube. Well, because if I was to try to make a longer standing wave, let's just think about the displacement nodes and the displacement aspect of the sound wave. Well, in that case, maybe I'd want an antinode at the end, which I know is the rule because the molecules have to be free to move at the open end. Well, in that case, I'd say, okay, well, then I have to get a displacement node somewhere. Well, if I move the displacement node over here, making the wave longer, that's fine and all, because then I'd have something that looks like this. But then I wouldn't have an antinode at the other open end. I'd have something in between a node and an antinode, something in between total destructive interference and total constructive interference. And that can't work. I can't have a partial antinode at the open end. I have to have a complete antinode at the open end. And so by following that logical rule that all open ends must be displacement antinodes and pressure nodes, then you know that the longest possible standing wave that exists on a tube with two open ends looks like this. And how long is this wave? Well, it turns out that the wave is exactly twice as long as the tube. Because look what we're looking at here. We're looking at half an oscillation. And I wrote it here as the tube being half as long as the wavelength, but obviously that's two ways of saying the same thing. I could also write that the wavelength is twice as long as the tube. Okay? So that's the longest possible standing wave that can exist on a tube with two open ends, called the fundamental or the first harmonic. All right? And then obviously you can create shorter waves that follow the same rule of always having displacement antinodes at the open ends, having displacement nodes that are always going to be a quarter wavelength away from those displacement antinodes and are going to coexist with a pressure antinode, and to follow the rule of having pressure nodes at either end. You can follow those rules and you can draw shorter waves. And we'll look at some examples of higher harmonics that can exist in a tube with two open ends. And I keep mentioning that there's the rule of pressure and the rule of displacement, but it's really an or situation, not an and situation. In other words, you can approach the wave thinking about its displacement and remembering to put antinodes at the end and a pressure node in the middle if it is indeed the fundamental. But I said a pressure node, I meant a displacement node. But at the same time, you could completely ignore displacement and the rules of displacement and just remember that pressure nodes must exist at the open ends and a pressure antinode must exist in the middle. So it's really an or situation. You understand that? You either think of the sound wave as a pressure wave or you think of it as a displacement wave, and it's up to you which rules you want to follow. And most of the time, more likely, you're just going to be using the formulas that I'll present that allow you to relate lengths of pipe to frequency of the wave and velocity of the wave. Okay? Now, let's briefly, since I think we covered most of the basic ideas, cover the other type, which is where you have a tube that is only open at one end. Because now we'll follow the same rules, but look how they look now. Let's start by just thinking about pressure. Well, we know open ends must be pressure nodes, okay? And that means if we have a pressure node there, then the closed end, what do you think the closed end should be for pressure? Well, it's a pressure antinode. It represents a point where we're going to have maximum variation away from atmospheric pressure. The molecules here could both be very high pressure and very low pressure. They can be condensed and they can be rarefied, okay? And if we think of displacement, then obviously the molecules that are lined up at the very edge, well, they're free to move, right? They can slosh back and forth, so it's a displacement antinode at the open end. But the closed end, well, the molecules are literally pushed up against the wall, so this is very much a displacement node. So in either way we think about it, how much of a wave do we have? We only have a quarter wave now, right? Or really, that means we can fit a much longer wave inside a tube that has one closed end and one open end. So now the fundamental is 4 times longer than the tube, or the tube is 1/4 as long as the fundamental frequency, because the wavelength here is the fundamental wavelength. All right, that's the longest possible wavelength that can exist inside a tube. In this case, inside a tube with one closed end and one open end. So we see that the fundamental for tubes with one closed end and one open end is longer than the fundamental with tubes with two open ends. And we won't talk about tubes with two closed ends. They would actually have the same rules as two open ends. Okay, if you were wondering. So there's really kind of the idea of what a node is, what an antinode is, what pressure nodes are, and what displacement nodes are. All right, for a sound wave in a tube, like a wind instrument. Okay, and by the way, closed end and open end would be like an organ, whereas again, as I said, two open ends is more like a flute for comparing it to real life instruments. All right, so there's some of the basics. Let's get into the key formulas to illustrate this idea in a little bit more of a concrete way. All right. Okay, so looking at our first key formula here, we have, all right, I forgot I was going to show you the string first, and that's, I'm glad I'm showing you the string. Sorry for being out of order. So if we look here, we have a picture of a string, okay? And looking at the string, we can see that we have kind of a similar idea of thinking about nodes and antinodes and such. But here, what's different is that it's not the sound wave that's traveling, so it would make no sense to talk about pressure nodes. So the string, in a very real sense, is a simpler concept, because in a string, you only have nodes and you have antinodes. And nodes are quite literally points where the string is not moving. It is staying at the rest, the point it would be at if it was at rest, okay, as if there was no wave traveling, no mechanical wave traveling back and forth along it. And an antinode is a point of maximum amplitude. Now that amplitude is still going to pulsate. It's basically going to actually move up and down like a harmonic oscillator, but it's going to move up and down between positive amplitude and negative amplitude. Now there's going to be other smaller harmonic oscillators at any other point on the wave, on this standing wave, but they're not going to have that same maximum amplitude, right? They're just going to have a smaller oscillation. But the point being is that this is your standing wave. In this case, we have a standing wave with a node at either end because the ends of a string with fixed ends will always have nodes. Just like the end of an open pipe is always a pressure node, the end of a string where it's attached to something is always a node, okay? And then antinodes will always be 1/4 of a wavelength away from every node. So that means that you would have a particular harmonic like this. And you might wonder, what harmonic is this? Because we were talking about the fundamental, the longest harmonic that can exist. Well, it turns out that this harmonic here is the third longest harmonic that can exist. Because the longest harmonic that could exist would look like this, with 2 nodes at the end and only 1 antinode. The next longest would just be 1 full wavelength, so it would look like this. Okay, that would be the second harmonic. And the one we're looking at here is the third harmonic. It's the third longest wave that can possibly exist on this particular string of that particular length. And it has a wavelength, as you can see, of 2/3 the length. See that? All right, so the third harmonic has a wavelength, so we can say that lambda 3 would equal 2/3 of L. Okay, so the third harmonic is 2/3 as long as the string that holds that harmonic, that holds that standing wave. Again, understanding that a standing wave is the superposition of 2 waves, one traveling to the left, one traveling to the right. Okay? Now you can actually easily count the harmonic by just counting the number of antinodes, because the number of antinodes always equals the order of the harmonic. You can also count the number of nodes and subtract 1, and that will also be your order of your harmonic. Okay? All right. So there's a wave on a string. Again, simpler concept because we can just say nodes and antinodes and we don't have to bother to say displacement nodes and pressure nodes and so on. Okay? All right. So now let's finally look at those equations. All right? So first of all, we have string length. This is the L that keeps showing up in the figures, either of the tube and the string. Okay? All right, so that's L. Okay, so again, this would be directly related to the picture. I just want you to think about strings. We'll get back to tubes in just a second. So notice the idea, excuse me there. Notice the idea for the harmonic, okay? So this is L equals n/2 times lambda n, okay? So n is the order of the harmonic. Harmonics start at 1, which is called the first harmonic, which has a special name, sometimes of being called the fundamental. You can call it the first harmonic if you want, but it's often called the fundamental, okay? And then lambda sub n is the wavelength of the nth harmonic, the nth order harmonic, okay? So for example, for the first harmonic, we see that lambda 1 would just equal 2 times L. It is exactly twice as long as the string. Well, where did we see that before? We saw that for the tube with 2 open ends. And that's no coincidence because all the rules that apply to strings also apply to tubes with 2 open ends. So that's a nice relationship you can remember. Tubes with 2 open ends are functionally the same as strings because strings always have fixed ends. Okay? All right. And then we can have a similar relationship thinking about the length of the tube and so on, but instead of thinking about the wavelength, because when we talk about sound, we always conceptualize sound as pitch, and pitch is measured in frequency in hertz. So we obviously want to be able to do that. Think about the string and the tuning the string at a particular frequency. So we want the frequency of the harmonic, okay? And that's what F sub n is, okay? And to go from lambda to the frequency, we use the relationship that the velocity of the wave is equal to the wavelength times the frequency, okay? And so that allows us then to talk about the frequency of the nth harmonic, okay? And the really neat thing here is that since we are talking about waves on a string, the velocity itself is dependent entirely, if you recall back when we talked about traveling waves on strings, on the tension of the string and the linear density of the string. Please review the previous lecture if you're not familiar with that formula there, okay? And so that actually has the very simple relationship that once we simplify this, that actually the frequency of the nth harmonic is just n times the fundamental. Quite remarkable. So it ends up just being basically a multiplication series in terms of the harmonics if you're looking at the frequency. Okay. So as I said, we bring it back to tubes. So let's go ahead. Oh, and by the way, that f sub 1 is the fundamental frequency. Okay, that's because any subscript there will just tell you the order of the harmonic. Okay, and a 1 is called the fundamental. If it was the second, I'd call that, I would say that's the frequency of the second harmonic. Okay, if there was a 2 in the subscript. All right. So as I said, I would bring it back to tubes. So pointing out here, this set of formulas also applies to tubes with 2 open ends. So we'd use all the same formula, just the L there would represent the length of the tube as opposed to the length of the string. Okay, but we have a whole separate set of formulas for the special case of tubes with 1 open end and 1 closed end, because they're the odd ones out. Okay, so these formulas only apply to tubes with 1 open end and 1 closed end, because we saw before, they allow for a longer fundamental, a longer wavelength relative to the length of the tube than either strings or tubes with 2 open ends. So their formula ends up being that L, the length of the tube, is equal to n over 4 times the fundamental frequency. Okay? So that tells us, well, I say fundamental, but it's really the nth order, and it's not frequency, it's the wavelength. So let me say this again. So the length of the tube equals n over 4 times the nth order wavelength. Okay? And if n was 1, then that would be the fundamental wavelength. Okay? And that tells us that lambda of 1 just equals 4 times the length of the tube. The tube with how many open ends? 1 and 1 closed end. Okay? And then then we can use the same relationship using the definition of wave velocity as lambda times frequency to rewrite this in terms of frequency. And we actually get the same relationship that the nth order frequency is just n times the fundamental frequency of that standing wave. So that relationship still holds, even though the wavelengths are longer relative to the length of the tube. But there's one other odd thing we have to remember, and it's literally odd, and that's that only odd order harmonics are possible for tubes with 1 open end and 1 closed end. Because you can think of them as being fundamentally asymmetric, and being such, they don't allow for the symmetric harmonics. It's just impossible, because the symmetric harmonics would force them to have the either 2 antinodes at either end or 2 nodes at either end, whether you're thinking about the pressure aspect or the displacement aspect, and that's just not allowed, because if we're thinking about either pressure or displacement, we know we have to have the opposite phenomenon at either end. We need to have, in the case of pressure, a node at one end and the antinode at the opposite end. And that means that only the odd order harmonics are supported. Okay? And so you can't actually talk about the second order harmonic for a tube with 1 open end. You go from the fundamental to the third to the fifth to the seventh and so on. Okay? So kind of important little detail to remember. All right. So there's our background. I tried to just kind of jump right into the important aspects that we need in order to understand standing waves. So now let's look at the types of problems that we would see involving standing waves in either tubes or on strings. All right, example 1. A 2.5 meter long string vibrates at 100 hertz with a standing wave with nodes at 1 meter and 1.5 meters from one end of the string, and no points in between those two. The string has 2 fixed ends, okay, which all strings do. Which harmonic is this? Okay, so standing string, because let's think about this, right? We know that the total length of the string is 2.5, and we know we have the frequency, which we'll need in other parts of the problem. But all we need to answer part A is realizing there's a node at 1 meter and there's a node at 1.5 meter. That means that the 2 nodes are 0.5 meter apart. Well, what distance are nodes apart? Nodes are always 1/2 of a wavelength apart. That means our wavelength must be 1 meter. Do you see it? All right. So let's think about this, right? So here it is written out. So the length of the tube is 2.5 meters. We know the distance between nodes is 0.5 meter, and we know that 0.5 meter must be half a wavelength, okay? Because the difference between nodes is always half a wavelength. You see it? The distance between nodes is always half a wavelength. Look, this is a full wavelength. A full wavelength covers 3 nodes. The distance between 2 is always half a wavelength, right? And that's true of any type of wave on any string or any tube. Okay, so that tells us that our wavelength is 1 meter, okay? So then we can say, okay, well, knowing that, then we're going to go look at our length of the tube and solve for n, solve for the harmonic, okay? All right, and look, right, so we know we fit 1 here, we fit another full wavelength, and then we fit half a wavelength. Well, if I have that many waves that fit this, and this is a picture, right? You don't necessarily need it, but it sure helps, right? Because we can go ahead and just solve this formula for n, right? If I plug in the length, if I plug in the n, and I solve for n, I get 5, right? But look at the picture, okay? So it's up to you, right? You can actually draw the picture to figure this out, right? Because I just draw, right? Okay, I know that's 1 meter, and then I know that's 2 meters, and then that's 2.5 meters. Okay, so that must be the standing wave picture. That's consistent. And then I just count the number of antinodes: 1, 2, 3, 4, 5. Ah, okay, n equals 5. It's the fifth harmonic. And indeed, the equation backs it up. Okay? All right, and there's the picture. All right, in part B, what is the string's fundamental frequency? Well, now here we're actually going to use the 100 hertz. All right, so we know that F5, the fifth harmonic, corresponds to the to 100 hertz. And we know that the relationship between the fundamental frequency and the nth frequency is just f sub n equals n times f1. So that means that 100 hertz equals 5 times f1, which means that the fundamental frequency is 20 hertz, just 1/5 of 100. Okay? All right. And then part C, what is the speed of the traveling wave on the string? Okay, well, since we know the wavelength of the fifth harmonic and we also know the frequency of the fifth harmonic, then we can simply say, oh, well, then we got enough information. Wavelength times frequency is speed. So that means that the speed is 100 meters per second, okay, which is pretty typical of speeds of waves on strings. They do tend to be pretty fast, especially if the linear density isn't particularly high, which it isn't for things like guitar strings. And then finally, if the string has a linear density of 200 grams per meter or 0.2 kilograms per meter, what is the tension? All right, we got enough information now. We got V, and so we only need to solve for the tension. So we set up our relationship that the speed of a wave on a string is equal to the square root of the tension over the linear density. Solve for the tension by squaring both sides. So velocity squared times linear density, represented by the Greek letter mu. And we get 100 squared times 0.2, which is 2,000 newtons, which is a fair amount of tension, actually. Okay? But there's the idea. And actually, this problem is good. It encapsulates a lot of the things that we'd be thinking about with a standing wave. Okay, especially one on a string. All right, well, let's continue on. I want to illustrate these ideas so we get some practice with them. Let's do some concept questions, right? Because most of this is conceptual. You can see that the actual equations are more like just kind of counting tools. They are not actually complex equations. You just got to remember that you just got to get used to remembering the rules, and then you're good as far as standing waves are concerned. Okay, so the figure below shows a standing wave on a string. It has a frequency f. Okay. What harmonic is that, by the way, right? I bet you can tell me, okay? Say it to yourself. What harmonic is shown here, okay? So draw the standing wave if the frequency is changed to 2/3 of f, okay? So we're just going to take this information, know that it started at f, and then know that we're changing up to 2/3 of the original frequency. Okay, how would we do that? Okay, so now we'll call that f prime, the new frequency. It's 2/3 of the original frequency. And then frequency, by definition, is the reciprocal of the wavelength, okay? That's what it represents. And so then we can rewrite this as the reciprocal of the new wavelength equals 2/3 times the reciprocal of the original wavelength. We know that the velocity is a constant because nothing about the string has changed, neither its tension nor its linear density. Okay, that's why we're able to cancel it out, because there would have been a velocity up here, but we just canceled it out. Okay, and so that means that the new wavelength is 3/2 the original wavelength. See that? So taking the frequency and changing it by 2/3 is the same as changing the wavelength by 3/2. Well, if the new wavelength is 3/2, then it has to be like half again as long. Well, if I have a wavelength that is half again as long, that means that it would look like this. See it? Right? That's a wavelength that's half again as long. Okay? Well, how many would fit now? Just 2. 2 full wavelengths exist. Okay? All right? So that's our new standing wave. All right, and I'll finally tell you what the harmonic was. This one was the 1, 2, 3, 4, 5, 6th harmonic. And now that we have changed the frequency by 2/3, thus increasing the wavelength by 3/2, now we have the 4th harmonic. We went from 6th to 4th. Okay? All right. Now part B. Draw the standing wave if the tension in the string is quadrupled, but the frequency is held constant. Okay? All right, well, the tension, that's going to affect the velocity. Okay, so if we consider the new velocity as v prime, well, then that's going to be the square root of 4 times the tension over the linear density. Well, the 4 comes out of the square root, because you take the square root of 4, you get 2, of course. And then this square root is just the original velocity. So that's telling us that the new velocity is actually twice the original velocity. So in other words, tripling the tension doubles the wave speed. Okay? So that means that if we go back to the definition of wave velocity being wavelength times frequency, then we're going to have the new velocity equals a new wavelength times the original frequency, because we're told the frequency was held constant. Okay? Then we're going to replace the new velocity with twice the original velocity because of the relationship that we showed in the previous line, which then allows us to then solve for the new wavelength and find out that it's twice as long as the original wavelength. Okay? So increasing the tension, in this case, quadrupling it, doubles the wavelength. Pretty neat, right? And if we double the wavelength, then what standing wave would we have? Well, now, let's think about it. If I'm doubling the wavelength, now I have a standing wave that looks like this. Okay? Well, how many will fit in this case? Well, just 1.5. Well, if I just fit 1.5 wavelengths on my string, that means I have 1, 2, 3, 4 nodes, or 1, 2, 3 antinodes, which means I have the third harmonic. Okay? All right, but we were just asked to draw the picture, but it's good to identify what the harmonic is. Since it is so easy, after all, you just count the antinodes, or count the nodes and subtract 1. Now, suppose the tension is merely doubled while the frequency remains constant. Will there be a standing wave? Right? Can you always get a standing wave? Let's see. Well, in this case, we're just going to use the same relationship using the definition of velocity on a string. And in this case, we doubled it, which means the root 2 comes out, which means that the new velocity is root 2 times the original velocity. And so then using the same relationship between velocity, wavelength, and frequency, then we can solve for the new wavelength. And we find out the new wavelength is root 2 times the original wavelength. Well, that's a problem. How am I going to fit root 2 times the original wavelength? Well, I can't, right? Because that's like 1.4 times the original wavelength. Well, if I get a wavelength that is 1.4 times as long as the original wavelength, right? Then I'm going to get something that, it's not quite 1.5, right? And so I'll get something that is, that's like this, right? But then it's not going to fit. I'm going to hit the end, and it's not going to be a node or an antinode. Well, specifically, it's not going to be a node, and I can't hit the end of the string and not have a node. That's against the rules. So that means that it's impossible. It wouldn't fit smoothly on the string. You have to have even multiples of half wavelengths to fit on the string, because you always have to get back to a node. Otherwise, no stable standing wave is possible. This would not create a stable standing node, and a manipulation of the tension like this would just create basically a traveling wave that would vary. So you'd have kind of so it would look like an unstable standing wave. You'd have locations that would appear like a node for a moment, but then they would transition slowly into an antinode and then back to a node and so on. That's not a standing wave. That's just two waves that are interfering with each other in a complicated time-dependent manner. Because there'd still be the waves reflecting back and forth, so you still have a wave traveling left and one traveling to the right, but not a standing wave. Doesn't meet the criteria. Okay, all right, so let's look at another example. Two sinusoidal waves, each of wavelength 5 meters and amplitude 10 centimeters, travel in opposite directions on a 20-meter long stretch string that is clamped at each end. Excluding the nodes at the ends of the string, how many nodes appear in the resulting standing wave? Okay, so let's think about how we'd approach this. So, by the way, the 20 meters is supposed to be scale. I think that it didn't get scaled properly. So 20 meters is the whole length here, all right? And we're told that a wavelength is 5 meters, okay? So then we can say, okay, well, in that case, right, if I have 5 meters, then I'd have 5 plus 5 plus 5 plus 5, right? So then 4 full wavelengths would exist. If I have 4 full wavelengths that exist, well, that means that I have 1, 2, 3, 4, 5, 6, 7, 8 antinodes, okay? And so then the number of interior nodes is 7, because we weren't asked for the order. If this is the 8th harmonic, okay? But we were asked for the number of interior nodes. That means excluding the 2 nodes on the ends. And so that is 7. The specific question was asking for the number of interior nodes, and it's 7. You see it? So this one's very much about drawing the picture. Okay. So when a certain string is clamped at both ends, the lowest 4 resonant frequencies are 50, 100, 150, and 200 hertz. When the string is also clamped at its midpoint, the lowest 4 resonant frequencies become what? Okay, so let's think about this. Okay, so the idea here is we know that the relationship between frequency and velocity and length of the tube is this, okay? And so we know if it's clamped in the middle, then we're going to have a frequency of 50 hertz, okay? And so then we can find, and our new length is 1/2 the original length. And so then we can find the new frequency and find out that F1 prime will just be twice the F1 where we had, which was the lowest frequency that existed on the previous string, because the 50 hertz, by the way, was the fundamental. And so now we have, right, so now we have a fundamental that is twice as long. All right, so now our lowest four frequencies are going to be starting with the fundamental 100 and then going from 100, 200, 300, 400, and so on. Okay, so clamping at the middle doubled the frequencies, because the frequencies still have that relationship where the nth frequency is n times the fundamental frequency. It's just that our fundamental frequency was doubled, thus all subsequent frequencies are as well. Okay, all right. Okay, so now we have a clarinet is a tube open at one end and closed at the other. Okay, so now we're going to tubes and moving away from strings. If this instrument is 0.34 meters long and is played at 20 degrees Celsius, then what is the difference in frequency between the fundamental and the third harmonic? Okay, all right, so we have the length. We're going to find the velocity of sound at that particular temperature. Here we're using the Celsius formula instead of the Kelvin formula, and we get a velocity of sound of 343 meters per second at 20 degrees Celsius. Okay, then we're going to use our formula that relates the frequency, the nth frequency, to the wave velocity and the length of the tube. And so then the fundamental will just be F1 times the velocity divided by 4L, and then F3 is just going to be 3 times the velocity divided by 4L. Okay? And so then we can just find the difference. We'll factor out the part that they both share in common, which is the V over 4L. And by the way, remember this V over 4L is unique to tubes open at one end. Okay? Otherwise it would be V over 2L if it was a tube open at both ends. Okay? And then the difference here is that our N went from 3 to 1. So we're just, that's going to be our difference. And so then indeed we can plug everything in. We'll just, of course, 3 minus 1 is 2, so I'll pull that out in front. Our wave velocity as calculated by the temperature formula is 343 meters per second, 4 because it's a tube only open at one end, and then the L was given as 34 centimeters. And there we have it, a frequency difference of 504 hertz. The frequency difference between the fundamental and the third harmonic. And notice I asked for the third harmonic. Had I asked for the second harmonic, that would make no sense because the second harmonic does not exist on a clarinet, because second harmonics don't exist on tubes that only have one open end. Okay, so question 2. Two pipes are each open at one end and closed at one end. Pipe A has a length of L and pipe B has a length of 2L. What harmonic of pipe B matches in frequency the fundamental of pipe A? Okay, so the idea here is we want to set the two frequencies equal to each other. We'll simply use the formula for the relevant harmonics, okay? Except we don't know one of the relevant harmonics, and we know since they're both, tubes open at one end, then we can have 4s that cancel out, right? 1 is twice as long, so we're going to have a 2 that survives, but obviously the L cancels. The velocity of the wave cancels as well. So then we can see that we're just left with N equals 1, or N over 2, see, equals 1, cross multiply, and we get N equals 2, all right? But that is not possible, okay? It can't happen. It's a trick question. There is no harmonic of pipe B that matches the frequency of the fundamental of pipe A. It just can't happen. Okay? Now, if I asked for it to be 3 times as long, then we'd be okay. Okay? But 2 can't happen. All right? Pretty cool, right? All right, question 3. A standing sound wave has a wavelength of 3 meters. What is the distance between a pressure antinode and a displacement antinode? This is a great one. I'd recommend pausing the video if you don't remember this, because this is just a basic question on the definition of pressure nodes and displacement nodes for sound waves, like standing sound waves in a tube. Okay, what's the gap between them? A quarter wavelength. Okay, it's always a quarter wavelength distance, physical distance between any pressure node and a displacement node. Okay. All right, so that means that if the wavelength is 3, it's a quarter of 3, so it's 0.75 meters. Okay. All right, yet another concept question. Organ pipe Y, open at both ends, is half as long as organ pipe X, which is open at only one end, as shown. Okay, so you can see X, right, has the one closed end, Y is open at both ends. Okay. What is the ratio of the fundamental frequencies of pipe X to pipe Y? Right? So straightforward question. Let's do it. Okay. So we know that X is twice as long, okay, as Y, so we'll call it L and 2L. So we have a great way of comparing them algebraically, okay. And then we'll think about the fundamental wavelength for the longer tube, the one that only has one open end, and that'll be 4 times the length. But the length is based on our system called 2L, okay? So that means that the fundamental frequency would be 8L. In other words, the fundamental, if I said frequency, but the fundamental wavelength would be 8L. In other words, 8 times longer than tube Y. So really long. And that makes sense again, remember, because the fundamental, if I'm going to draw it in terms of pressure, let's draw it like pressure, the fundamental would look like this, okay? And that's only a quarter of a wavelength. So that means the actual longest possible wavelength that exists in tube X is really long, right? It's longer than would even fit on the screen, okay? So let's do the same thing for tube Y, okay? Well, since this is one of 2 open ends, the formula says that the fundamental wavelength is only twice as long as the tube. So, okay, so then it's only 2L. So we see there's actually a big difference, right? One is 8 times as long, one is only twice as long, okay? And then if we want to compare their frequencies, because after all, we're asked for their frequencies, and since these are tubes that are in the same room, so they're going to have the same velocity, then we can compare our relationship. So take a ratio of the fundamental frequency of tube X to the fundamental frequency of tube Y. And what we're going to get then is 1 over 8 equals 1 over L, because everything else cancels. And that means that we have a 4-to-1 ratio. All right. So in other words, the fundamental frequency for tube X is 4 times as high. So it would be a much higher pitch. Okay. And that makes sense because shorter wavelength, and it is, after all, 4 times as short, right, means higher pitch, because as wavelength goes down, if velocity is held constant, frequency goes up. So this one has a high frequency and this one has a low frequency. Okay. All right. Last example. 2 tubes are filled with air at a temperature of 20 degrees Celsius. Tube 1 has a length of 1.3 meters, is closed at one end, and is sounded at its 5th harmonic, n equals 5. Tube 2 has a length of 1.5 meters, a little bit longer, and is open at both ends, and is sounded at its 3rd harmonic. What temperature would the air have to be in tube 1 so that these 2 tubes produce the same frequency sound? That's kind of cool, right? All right. So we're going to use this formula here, okay? This is, again, is the formula for the velocity of sound based on Celsius. You could also use the one based on Kelvin. Either formula is totally valid, okay? They're both approximations and they both give you about the same number, okay? And so for the tube with 2 open ends, which is tube 2, I'm just going to start with that one, okay? Then let's consider it, okay? So then we're going to use our formula here to relate length to a particular order harmonic and the particular wavelength of that order harmonic, and then also use the formula to relate the frequency of a particular order harmonic to the velocity and the length, okay? So then we know that the frequency of the 3rd harmonic is 3 times the velocity at 20 degrees times 2 times 1.5 meters, or a value of 343 hertz. Okay, great. There we have the 3rd harmonic in the tube with 2 open ends, okay? Now, the reason it might make sense, and the reason I did start with tube 2, is because we're not doing anything with tube 2. We're not manipulating tube 2, right? The only thing we're manipulating is the temperature in tube 1. So that means we're going to take this value, set it equal to the conditions for tube 1, and make our variable, yep, the temperature, okay? So now for tube 1, which only has 1 open end, okay? Now we'll use the relevant formulas, the one where the fundamental is 4 times longer than the tube, and the frequency is 1/4 n over v, okay, and so on, okay? And we know we want it to equal 343, the value that we calculated above, okay? And we know we want it to be the 5th harmonic, the frequency of the 5th harmonic, okay? And at 20 degrees, the frequency in the tube is going to be 660 hertz, okay? So we know it's not going to be the same temperature because 660 and 343 are not equal to each other. And we don't need this step. I just want to point out that it doesn't work if they're the same temperature. They have very distinct frequencies. Okay? So that means that we're going to have to do something, right? We're going to have to, well, lower the temperature, right? Because we have to make this frequency less. Okay? So that means we need to solve for T needed for tube 1. Okay, so here we go. We set it up. It's the 5th harmonic. It's a tube open at one end, so it's 4 times L. L is 1.3, so all stuff we know. All right, and we know we're setting it equal to 343 because that's the value that we need to equal for tube 2, the one of 2 open ends. And then just solve for our variable, solve for temperature. All right, here I'm just doing the algebra, walking through the steps. All right, and we get 42.9 degrees Celsius. Okay. So let's see. It's actually a higher value. Why is it? Let's see. So we have Just thinking about this because I was thinking it would have to be a lower one because at 20 degrees we got a higher frequency, and so if we're making it, oh well, yeah, okay, so we did, I guess because we had to make the temperature higher in order to get the frequencies to match. Okay, but anyway, this was us solving for the temperature necessary for tube 1 in order to be sounded at the same pitch, in other words, the same frequency as the other tube. Okay, so good kind of variation on how you can work with one of these problems of standing waves in a tube. Now, this wouldn't work for a string, but a version of a problem like this for a string would involve changing the tension of one of the strings while not changing anything else about it. But of course, it wouldn't be quite as interesting because strings only ever have this one formula. They don't have the two different conditions depending on whether there's an open end or not. Okay? All right, well, anyway, this concludes our lecture on standing waves and also concludes the entire chapter on waves in their entirety. Okay? I hope this lecture has been interesting and informative, and thank you so much for watching.